Hello and welcome, and thank you very much for joining me today. The subject of today is resonance frequency and wave characteristics associated of it. I have prepared this short presentation today as a live streaming introduction. We will look for resonance frequency and see if the wave it draws on the oscilloscope does confirm that we found it. The test will be performed by a scatter configuration where the DOT is located between a two-winding amplifier coil on the left side, and on the opposite side a dipole antenna connected to the oscilloscope. So please add any questions you have in the chat window and I will go through them after the presentation. Now let's look at our test. So we locate a secondary Tesla coil in the center between the exciting coil and the receiving antenna. With the frequency sweep, we observe the performance of efficiency between excitation of the coil and its radiation. Last, we will identify what frequency is best to use for any application involving harmonics. This is based on a COP, or coefficient of performance. Now let's look at what equipment we're going to use. So we have the 3-channel desktop power supply from TDI, followed by the 4-channel 100 MHz oscilloscope from Keysight Agilent, and the amplifier consists of the driver circuit with a TC4421A, which is inverted, and the IXYS power MOS amplifier. Now let's go to the DOT of the device under test. All physical parameters here on this DOT is configured, is measured without the help of an LCR meter. In order to calculate the resonance, we would need to find the parasitic capacitance as well as inductance of the coil. The stray or parasitic capacitance of the coil results from the distance between each winding. This also changes over frequency. So the complexity of finding the correct resonance frequency is further influenced by dielectric losses of the former material, as well as a coating of the enamel copper wire and material in the closed surrounding. With this oscilloscope view, we measure the voltage peak values and trigger the signal via the built-in signal generator. So we're going to have here as well in picture the power amplifier, and here you will see then the measurements here on the right side. You will see then the power requirements for the triggering. Now let's have a look at the table. I switch over. Here in front of you, you see the setup arrangement. A 2-turn coil of 2 mm copper wire is the exciter coil, left, followed by the DOT in the middle, which is hovering over ground via nylon wires attached to the ceiling, and the dipole antenna as main probe of the frequency measurement on the right side. On top of the coil are 2 oscilloscope probes to show the overall wave characteristic of the unterminated floating coil. So I will now set up the system in order for us to identify the frequency, and we choose here as a frequency. I start the wave generator and I start also the amplifier and the signal. So as you can see here, we have, and I zoom in, we have here so 1 kilohertz signal. So in order to measure accurate, you start with a low frequency. If you go higher in frequency, measurements can change, will change, but here also we have some fluctuation. So Z is a coil which is fairly large, and therefore it has some fluctuation. So you see the measurement screen here on frequency 1. If I scroll through the measurement, you can read 1.86, 1.87 megahertz. So if I scroll through, it's around that range 1.5 megahertz. So it would probably shift here between 1.8 and 2 megahertz, but 1.5, 1.6 megahertz is the stable reading we have. Now let's go over the fundamentals. Here on the graphics on the right side you see the first fundamental on top. The quarter wave on the right would be visible when the coil is grounded. If unterminated, we see the wave fluctuation at the bottom left, where the center of the coil is close to zero. This would indicate a reflection wave with a node in the center and antinode at the end. However, please note that this is a pressure wave here because it is based on sound. It is also the longitudinal propagation of the dielectric fields of the wave. I will show another graphic to demonstrate that in a minute. So here's another view of what happens when the coil is excited. It is an example of the dipole antenna. Our test will demonstrate that we will see a half wave instead of a quarter wave. Here we measure only voltage, but at the zero position in the center of the coil, the current is highest. This can be proven by using a spectrum analyzer measuring the electromagnetic radiation in 3D in distance from the coil of at least 1 meter. I have posted recently a video to my members in my latest video to show that. So what we're going to do now, we're going to change the settings and I go up in the harmonics. Let me do that. So we start with a frequency of the so-called first lower harmonic. So the frequency would be around 468 kilohertz. And I hope you had a, sorry, I need to change here the view. You had to look at the power supply 1.6 watt. If you go to 468, so that's something I would like to bring your attention to, the power requirement at the various harmonics. So 468. So this is a quarter. Down here. So here you go. I auto scale that, and I fine adjust it. So here we have then 10 volt. I need to set that up to 10 volt as well on the green channel. So we have on channel 1. Channel 1 is the yellow line on top, and that is a dipole antenna. Channel 2 is the oscilloscope probe in the center of the coil, and channel 3 is the bottom, and we have here on channel 4 is the trigger signal. So I stop that for a second and I bring them both together. Wave music. So very important here, I use an inverted signal. There's no specific reason for that, but when you look at the duty cycle, you see 80%. So 80% is the opposite of a non-inverted signal. So technically, I have the lowest trigger signal, like 20% non-inverted. As you can see, I use one signal to excite technically 4 waves. And if you put them close together, you will see they're opposite in direction. If you have a look here, you can see that they're opposite in direction, and we have 0 in the center. So this is a wave characteristic of an unterminated coil. So I go further up now in the frequency. So that is, we have here a power requirement of 1.66 watt. Please take note. Now go further up to the next harmonic, which be third down, and this is a very, very important harmonic. The third harmonic is also called a very destructive harmonic because it causes a lot of resonance energy to be transferred, and that is actually here around 600 and no, where are you? Here we go. So we have now a power requirement of 0.88 watt. So if you looked at the peak-to-peak value we had on yellow, for example, on 3, so they might be around the same value, but you see we have only half of the power requirement currently. If I stop that again, now you can see that the trigger signal is shorter. That means we have one trigger signal and we only excite 3 waves with it. So we assert lower harmonic down of the resonant frequency. That is very important. Now let's go up to the next frequency. The next frequency will be the so-called half lower harmonic of the resonant frequency. Should be around 930. Let's go up. Here we go. So we still have peak to peak the same value. I stop that for a second. As you can see here now, my trigger signal is now activating or is like exciting only 2 wave cycles of the resonance frequency. And we still are at 0.85 watt lower. I can now increase the duty cycle. Let me do that to get it a bit up. Let's say we want to have, it's very close, 0.88. So the third lower harmonic and half lower harmonic are frequencies always used to trigger resonant frequency because there's the most efficiency from a coefficient point of view, the most efficient way to use power to excite a coil. So what happens if we now go higher up? What happens if we go now to the next level? So, okay, let's do that. Let's have a look what happens. So if we go higher in the frequency, we're going closer and closer to the trigger frequency, which is close to the resonant frequency. That means also, brings it back up to 80% duty cycle. That means also we require much more power to, go 1.8 watt. Okay, I have 20. As you can see, I have down 20.9 volt peak to peak. However, I cannot change that anymore because I'm already on the lowest value I can do here from a duty cycle point of view for an inverted signal. With a pulse, I might go slightly lower, but not by much. So I cannot find an exact value to that. Let me stop the signal. As you can see here, 1.5 waves currently from a trigger signal. Now the good guess would now be, what do you think happens if we go now to the resonance frequency? Will the power be at the same level? Will it be a little bit higher, or will it a little bit lower? Let's see. So resonant frequency 1.8, 75 today it wants, and we consume 6.7 watt for a slightly change only in the performance of the coil, but our power requirement is dramatically increased. So this actually was a very short presentation and then concludes my first presentation, and I would like to open the floor for some questions you might have. I'm going through here, so the questions, I haven't seen anything you would like me to test, to do, or any questions you have so far. I will wait for some questions you would like to ask. Let me just stop the power, it's getting a bit hot. No other questions? Do you want me to demonstrate something again to have a better view? No, I think we're going to wrap this session up, and I thank you all very much for participating. I will produce very shortly a new video for upcoming workshops I will do, where we're going to have this kind of meeting with a group from up to 25. What harmonic is most destructive? Oh, that's a very good question. So for harmonic we need to define technically every harmonic is destructive. So if you look at transformers and the way in the world we use transformers, then you will not find any transformer which works on harmonics. Because harmonics if you wouldn't have a transformer which uses a core material, the core material would vibrate extensively. And I use, for example, my Farad coils, and at lower frequencies they are getting so noisy that they can actually break. So the material can actually break. On a coil, so technically the only way you can get energy transferred between air coils is only via resonance. However, the problem here in resonance is that you have peak values along the lines that your Tesla coil is a transmission line where waves do exaggerate or do expose or get extended, as we see in this video. Let me show that again to you. It will be shown here at this node. So if this appears on the coil itself, you have a peak values. I mean, I have not used much power. It's very far away. It's 5 centimeters away from the coil. The scatter experiment is supposed not to influence the coil at all. And we don't have much power here. However, if I really excite this one, and I use hundreds of volts, and I use directly a primary coil, at that point, and I have done that before in other tests, I burn the cable. So the wire, and that was a thick wire, on a distance of 2 meters, did actually burn at specific points. And that's what you need to avoid. We can't have this one. Let me read my dear. Understand that you want to see the setup again? Okay, no problem. Let me switch over to the setup overview. Where are you? Okay, let me switch over. Okay, you see here, the scatter experiment is a classical experiment where a test device, this experiment is actually over 100 years old. So that was done in the beginning of the 19th century. You have an exciter which is outside of the coil itself in a distance, and you have a receiver on the other side, and here specifically the dipole antenna on that side. And you use a small coil, like here only 2 windings, it's a 2 millimeter copper wire, and you excite it. So that will definitely not influence it. If I would take the coil out, I mean, I can try to swing that for you if you want. Give me a second. I swing this coil and I show you that on the oscilloscope what happens. Let me go down also in the frequency a bit. Let me go first down oscilloscope. Let me get that up again. I go down the frequency because that is a bit it's getting very, very hot. Getting down to the strong value. Right. So I have this currently up. Now let me go now to the coil. Let me move the coil now and want to show you something. So you see now what happens. Now let me go now to the oscilloscope screen so you see what's happening. If the coil is not directly in the center, there is a 0 value of measurement. This is very important because you cannot influence the coil itself. You cannot influence it because it's an air coil. It is very, very sensitive to any material we get close to it. So if it's outside of the center of the measurement, there is no influence whatsoever. Even if I use very, very strong power amplifier on that side, nothing will happen here. Okay, now I need to go. Let me go back so you can see that is me. Need to go back to the question, like Bismuth plating over ein. Squeezing down on them. let me see what I get here. So is the let me answer this question from AR. Is that understood why to use a scatter experiment rather than using a test primary on it, because it would completely influence the results and you wouldn't be able to use this. You would get false reading. Even if I would use now a grounding wire, the grounding wire would show us now the quarter wave perfectly. However, it was also the frequency goes down by almost 30%. But that's what you normally can do as well. But then you would see the characteristic of the quarter wave. So you would see the fundamental. You would see the quarter wave. If I would ground it, you would see the quarter wave here as wave characteristic and not the half wave we have here, like in the bottom left, as it is seen here. So the maximum harmonic is the destructive, so the question from the maltodexter. Is there a maximum harmonic for iron core lamination? That depends on eddy currents, that depends on the strength of the material. So normally you laminate the core actually to avoid eddy current between them and current flux between them. But what you cannot avoid is, because of the crystal structure, you cannot avoid other losses and heating of the material. That's why you should use, normally, if you build a power transformer, you should use Metaclass. However, this is a very, very expensive material, but for high power applications with low losses, Metaclass is the only material because it's fluid. It's a fluid metal, if you want. It's glass. And because of that, it has no crystal structure, and therefore it does not have these losses of heating and so on as a normal crystal structure has. So to answer this question, it depends really on the core material. It depends on the strength. You probably all know QEP from Hope Girl, where they used an iron core transformer to create resonance in the core. So this would be an example where the core material is very much under stress. And if you would use a lot of power which goes over the capability of the material to deal with it, then this core would break. And it did break in tests they have done before. So I do not advise, very important, I do not advise to use harmonics with core materials, even so that the power transfer is very strong, but you will not have much fun of your transformer for long. That's why only air coils can be used with resonant frequencies. Right, okay, let's go to the next one. Oh, Cyrus of Lemuria has a question of what other use other than power transmission through the Earth, Tesla magnifying transmitter, what other uses does this technology potentially have? Well, one use I did demonstrate already, which nobody is using it actually, for communication. I did actually a couple of weeks did some tests. So that's an experiment with using an amplitude modulation via a Tesla coil, and because we're using resonance here for sending our signal, even a normal transmitter, all normal radio transmitter, they don't use resonance. Very important, you need to understand that there is no such thing that they can use it, because the transmission line is always done via a quarter wave line to the antenna, and therefore the antenna will radiate most of the energy, but that is not resonance. That is a frequency which has been adapted to it and is filtered. There is no resonance in that. It's just a purely energy transmission, and this energy transmission is not 100%. It is always less than the energy which you put in. However, in communication, that's a completely different subject. That's something I want to bring up in my workshops I will produce. There will be a lot of workshops coming. I will produce another video shortly where I'm going to explain to all the workshops I will produce this year, because in a workshop we can have this kind of communication where we interact and so on, and that is not consultancy, and therefore it's a different subject. However, we will be in a group and we can discuss that. We have a subject we can talk about, and then we can actually see how that pans out and how that works and so on. But for communication purpose, it's amazing, absolutely amazing. And I don't mean that you can penetrate metals or whatever. I mean that you need almost zero energy to transmit over a great distance. I haven't even tried hard, and I will demonstrate that in one of my workshops, which will coming up for communication. Next one. Oh, let me read some of the stuff other than Okay, from Thomas Anderson, another question here. Crystallized in random small crystals to avoid it being its own magnetic unit. The crystallization, because of the way the materials are hanging together, they create a bonding. And this bonding is, of course, allowing current to flow in special direction, but it creates also resistance. And the issue is the resistance. The crystal itself is not so much the issue. It helps you, it still gives you the opportunity to have a strong magnetic field saturated in this core material. However, the problem is the heating of the resistance. Because of that, there is the energy in there cannot flow like it would be in a supercooled environment, like in supralighting, yeah. And because this material, it gets very, very hot. And here you see, and you probably know that transformer cores in power stations, they're all located inside cooled oil. So they're all swimming in oil, in container and oil, and they have heating, have cooling environment around it to cool it because of this heating. However, a lot of power plants are using Metaclass technologies, and they can avoid all that altogether. You save a ton of energy by using Metaclass material. However, for small applications, it's not usable because it saturates the material so strongly that you need a high power, high stranded wire actually to use this Metaclass core to work with it efficiently. So in my experimentation, so when you go on my videos where I demonstrate that, it was not that efficient, and it actually was, compared to other core materials I used, was kind of disappointing. But I kind of expected it because it's 5 or 10 kilowatt core materials, and that power, of course, I did not use, and therefore I didn't efficiently use these core materials. So let me have two more questions, and then we have to wrap that up. Let's go for another questions here. Yes, I will bring up the communication from I will bring that up in a workshop, coming up workshops where I dedicate some time actually over many courses in a workshop for a specific subject when we go over a communication bit. I will do that. The Pancake coil is a complete different subject, and I didn't use it. I used this is a question here from AR. So the Pancake coil is a complete different subject. Reason being is that the magnetic flux, and the orientation of the magnetic flux is completely different to what happens here on a solenoid. Because rather than going in a length in a difference out, it expands in a vertical fashion. It doesn't expand horizontal, it expands vertical, and because of that, they don't interact in that fashion. However, when a bifilar coil or a pancake coil excites or a solenoid coil, the energy push is very strong. It's very, very powerful. That's why you see a lot of Tesla coils actually built with kind of pancake coil. It's not really, they're either going in a V shape or they are flat around it, going in the circular fashions. It's a kind of pancake coils if you want, because they're very, very powerful and excite the secondary coil much stronger than if you would use a normal primary as a coil in the same winding direction if you want. Last question. So from Mohammed, I don't understand this question. How can we achieve high frequency with high voltage through existing equipment? I don't understand this question. Of course you can achieve high frequency and high. So okay, high frequency in a coil depends on the size and dimension and the amount of wire and windings you have in a coil. If you want to have a high frequency coil in a megahertz range, you can use only a couple of windings. It has to be small. Also, the ratio between the windings itself to the distance, the width of the coil, the length of the coil, they need a specific ratio for the frequency. So the less the distance, and you remember maybe an experiment I did where I did show you with a scalar network analyzer how this frequency is actually then influenced, the frequency velocity is influenced by using the different winding distance and the diameter of the coil. You can actually influence the velocity of the speed of light. However, the velocity in the speed of light around the coil is never 100%. It's always maximum 82%. That's what we measure in a coaxial cable. It's less than speed of light. However, because of the longitudinal expectation, it's faster than the speed of light, because at this pressure wave we can move much, much faster, and that's what I did measure. So if you want to have high frequency via longitudinal fields or purely via dielectrical field, and that is not electromagnetic, via the dielectric field, very important, which has only the voltage component mainly to it. Here in my experiment, for example, we measured the dielectric field. We didn't measure the electromagnetic field. So the dielectric field was only the voltage we measured. We did not measure the electromagnetic. That would have to be done with a spectrum analyzer, and then you would have seen a complete different picture. So I posted that on for my members in a video where I did demonstrate that, and I watched a short video where I demonstrated that as well on YouTube. When you use a spectrum analyzer, you see only a couple of volt here in a close distance to that, but you have about 100 milliampere of current in a distance of 1.5 meter. How does that pan out? Because there is an opposite reaction between the electromagnetic field and the dielectric field on the coil, and this of course has an influence of what happens. And what is responsible, or what is important for us for communication, the electromagnetic component is important, not the dielectric component. The dielectric component is what makes the coils then creating sparks, yeah, or any kind of flashing or whatever you want. That is the electrical component. Both work together, yes, but independent are exposed in the environment. So that's very important. So one more question. Okay, one more question. Let's have a look. No, I just explained here. That is from Skull Tracer. So the megahertz response to a coil. Okay, there's another subject on it. What you have seen here on oscilloscope is of course the resonance, but it's in the so-called time domain. So this time domain is only as a fraction of a time when you see the peak values of the crest and the draft of the wave, if you want. However, what you have not seen is the spectrum at what actually happens. If I have a specific frequency and I triggers this coil frequency, what happens? If I take 1 kilohertz, what happens? How does it look on a spectrum analyzer? When I take 1 megahertz, what happens? And there's a huge difference what happens. That's something I have produced as well on a video, and I will put that also in a workshop, because that is very, very important, because we can influence here things, and we can influence actually the functionality of a Tesla coil with very, very small pieces without changing the whole setup to make it resonate in a specific frequency. But that's a subject for another time for this video. And I'd like to thank you very, very much now. I like to wrap that up, and I hope I find you soon all participating in my workshop, and wish you all a good night, good morning, or wherever have you been. Goodbye.